Okay, so I'm sorry I have to wear a mask. I don't have to, but you know, my brother came down with COVID, which we found out after he'd stayed at my house for 3 days and went home to Maine. So I tested negative 2 days in a row, but so did he. So just I don't want to get everyone infected in time for finals week. So I just decided to wear a mask. I hope you can hear me. Can you hear me?
Yes.
All right. All right. So anyway, I just want to say the final exam is December 14th. It's in this room. Just a few words about the final exam. I just want to say that there is some material that's not going to be on exam 3. Some of the stuff we did last time, the geometry stuff, is not on exam 3. We're going to finish that today. And some of the stuff, we're not going to do a whole lot with chapter 8, but we're going to do some, and that'll be on the final as well. But since you won't have been tested on that already, I will have some problems on the final that you will have to do from the latest material. For the rest of the material, which is a cumulative final, but I have some choice built into the final so that you will not have to do every single problem. In fact, there'll be considerable choice. So if you don't want to study a particular topic that you've already been tested on, you probably could get by, you know. How do you know? You don't know. I'm sorry. If you need to know, then you better study everything. Okay. Also, the earlier material, you're going to find it easier probably than you did back then, I hope. Anyway. All right. So anyway, that's enough on that. I'll have to post some more information about that. I do want to tell you that for the exam on Thursday, I have a front page of the exam that has equations. It does not have the 1 over lambda equation, the Rydberg equation thing. It has this equation, delta E equals minus 2.18 times 10 to the minus 18th joules, 1 over nf squared minus 1 over ni squared. Oops, wrong square there. Okay, it doesn't have the one that you used in lab with the Rydberg constant. Some people use this on the take-home quiz. Some people use that other one. This gives you, this is delta E atom. If you take the absolute value of this, that's the energy of the photon that's emitted if this is an emission, or required if it's an absorption. That photon energy can give you the wavelength, because and this equation is on the exam, this one. And if you know this, then you could find the wavelength by just rearranging this equation to lambda is hc over E photon. So you can use that, and that's what you would have to do if you were asked to do the same type of thing, finding the wavelength of a transition in hydrogen. So just look at that, okay? So some of you who took the optional quiz, it seems to have major grade lower, but I won't do that for you. It was optional, so I'll give you whichever was better, either the 2 out of 3 of the first 3 quizzes, or 3 out of 4, including the last one, dropping 1. So you're not gonna get a worse grade because of having taken the optional quiz. So last time we started to talk about geometry of molecules. And we talked about, and what you have to do, what this all starts with, is examining the number of groups of electrons on the central atom. So this really only works for pretty simple molecules, although we can consider different atoms in a molecule as central, and we can consider the geometry like that. But in this course, we're basically doing fairly simple molecules. And what we did last time was we looked at what happens when you have 4 groups of electrons on that central atom. And when you have 4 groups of electrons, it's like you have like 4 balloons tied together in the middle. And just like electrons repel each other and want to get as far away from each other as possible, these balloons also can't take up the same space. Okay, you can't put two balloons in the same exact space. They will repel each other by not being able to get into the other balloon. All right. So when you have four groups of electrons on the central atom, you will have something that looks like this. And in a good example of a molecule that is like this is methane. So if I just try drawing this, my four sort of groups of electrons, and this one over here is overlapped a little bit. If I put my carbon in the middle and I put my hydrogens at the end of these balloons, and remember, I use a wedge for coming out of the plane of the overhead. Let me shut the lights off here a little bit. So that hydrogen that's at the end of the big wedge is coming forward out of the plane of the screen. And the one that's a sort of a dotted line going back, and notice it's a vertical dotted line. Okay, that's showing that it's going back into below the plane of the screen. Okay. And if you were to connect these lines, which I'm a terrible artist, but if you had this, let me draw it again. If you connect these, try to do it in a different color, maybe it'll help. What that shape is a tetrahedron. And the carbon is in the center of the tetrahedron. And when we draw, so a methane molecule, for example, if I told you to draw the Lewis structure for methane, you would count up. The carbon has 4 valence electrons because it's in group 4A or 14. Hydrogen has 1, but there's 4 of them. So add that together. You have 8 electrons or 4 pairs. And so you have a very simple Lewis structure. But in a way, that Lewis structure is lying to you, right? Because what is that Lewis structure telling you? It says, oh, methane, that's nice. It's planar. It is not planar. As you can see from this other diagrams, we go through great pains to show you that this is not planar, okay? So this is really not planar. So while this is the correct Lewis structure, it is not the correct way to draw it, showing the geometry. To do that, you'd have to do something like this. And what I always do is I use 2 single lines that represents in the plane of whatever you're writing on. And then you have the wedge coming out of the plane forward and the kind of reverse wedge going back. Yeah. What makes it get that shape is the fact that you have 4 groups of electrons trying to get as far away from each other as possible. And that's what it would be in space, okay? So let's see. So we say that the electron or electron pair, sometimes we don't use that word, pair, geometry is tetrahedral. Okay. Now, in the case of methane, CH4, so for methane, there are 4 atoms at the ends of each electron group. Let's see what that means. It's not so complicated. All that means is you have the 4 groups are bonds. So of course you have an atom at the end of each bond. So that means that when we talk about, so this is the electron geometry, we talk about the molecular structure. There are different words you can use. Molecular geometry. I tend to use the simple term shape. So these are all the same thing. And these tell you what the shape of the molecule is. And when you have an atom at the end of every one of those bonds, right, every one of those electron groups, then the shape of the molecule is the same as the electron geometry. So we say that the shape, or all of these things, whatever you want to call that, is also tetrahedral, because you have these four things at the end of the bonds. So it has this, it looks just like that, with the carbon in the center and the four atoms there. Okay, so in the case of methane, the molecular structure is also, I should say, tetrahedral. Okay, but then last time we went through a couple of different situations, because for molecular structure, what matters is where the atoms are, not so much where the electron clouds are. So, for example, we have ammonia, NH3. The Lewis structure for ammonia is this. I did do this last time, okay? And how many groups of electrons are there on this central atom? Okay, lone pairs is one group. Anything that's pointing in the same direction, these are both pointing in the same direction, it's one group. Then we have 2, 3, 4. So we have 3 single bonds and 1 lone pair. So that's 4 groups of electrons. So whenever we have 4 groups of electrons, we have a tetrahedral electron geometry. But now we do not have an atom at the end of every one of those groups. We have an H here, here, and here. Here's a nitrogen. Okay, so the shape is determined by where the atoms are. So if I just start like this, okay, it's exactly what I'm just drawing it a slightly different way. You can see that what you have here is a little pyramid with the nitrogen over here and the 3 hydrogens. So we call the shape, and of course the lone pair is up here, but that's not determining the shape of the molecule. That's just out there. There's no atom at the end of it. So what really matters are these atoms here, and they form what we call a trigonal pyramidal shape. So that's the molecular structure or shape. Well, because we don't count these, it's like this is cut off because there's no atom at the end. What tells you what the shape is the positions of the atoms, and there is no atom going up. So we say that the shape is trigonal pyramidal. So that's what happens when you have 3 single bonds, right here, if you look at the Lewis structure, and 1 lone pair. You end up with a tetrahedral electron geometry and a trigonal pyramidal shape or molecular geometry. These are all the same. It's just 3 different ways of saying the same thing. The book calls it molecular structure. I tend to call it molecular geometry or shape. They're the same thing. Okay, so what other situations can you run into with a tetrahedral electron geometry? If you write the Lewis structure for water, right, you have 2 valence electrons, 1 for each hydrogen, and 6 for the oxygen. That's 8. So again, you have 4 pairs. So now you have a bond to each H, and you have 2 lone pairs. So now you have 2 single bonds and 2 lone pairs. So how many groups of electrons is that on the central atom? It's 4. To determine the electron geometry, you have to look at the groups of electrons. So you have 4 groups of electrons. That means that you have a tetrahedral electron geometry. However, you do not have a tetrahedral molecular shape. In fact, you can see that what the shape of a water molecule is, it's just bent. You see that? So I could draw it this way with an O. I often call these Mickey Mouse diagrams. Okay. So for the shape, this is all I care about, is the positions of the atoms. So the molecular geometry or shape is just bent. Okay. The other one I showed you last time, move this down a little bit. This is, yes, I'm just getting this out of the way. So the other one that I talked about last time was for 4 groups of electrons. If you have like HCl, this is the Lewis structure of HCl. You have 7 electrons from the chlorine, 1 from the hydrogen. Again, you have 4 pairs, but you have only 1 bond, 1 single bond, and 3 lone pairs. Okay, when you only have 1 bond, there's only one thing this could be, and that is a linear molecular geometry. But the electron geometry is still tetrahedral because the Cl has 4 groups around it. No, I'm not ready to do CO2. CO2 doesn't fall into this geometry, so CO2 is linear. That's right, because it has 2 groups of electrons on the central atom. CO2 has this Lewis structure. So it has 2 groups of electrons. When you have 2 groups, your 2 balloons would be in 180 degrees to get away from each other. So we're going to do that one later.
So it will always depend on the electron.
That's what you have to start with. Absolutely. I'm not ready to do this yet either. Yeah. I wanted to go over the angles with you from last time because I already did this last time, but that's all right. So let me show you the angles. So when you have this tetrahedral electron geometry, this angle here, which is the same for all of them, you could see it's a little bit bigger than 90 degrees, but it's not 120 degrees. It's actually 109.5. That is the tetrahedral angle. Okay. Now, when you have a methane molecule where you have all, you have atoms at the end of every electron group, these angles are all 120 degrees. They may not look it, but that's because of the perspective, right? This is coming forward and that H is going back, and so it's a bigger angle than what it looks like. So here again, you have an electron geometry that's determined because you have 4 groups of electrons. It's tetrahedral. The molecular geometry is also tetrahedral. and you have the bond angle 109.5. That's when you have bonds from the central atom, 4 bonds. For ammonia, you have this situation. Okay. The electron geometry is, what's the electron geometry? Tetrahedral. You still have the 4 balloons, except that now you have a lone pair in one of those balloons. So your molecular structure, the molecular geometry or structure, is trigonal pyramidal. Okay. Now, what happens when you have a lone pair is that lone pairs take up more space. So they kind of push down on the rest of the molecule, and they make this angle, these angles here are less than 109. So they're a little bit less, so like 107. Yeah. Oh gosh, it shouldn't be 120. What did I do here? Is that what you were going to say? Yeah, I'm sorry. That's a bad mistake. You should get a gotcha for that. Yeah, I don't know why I wrote that. It's 109.5. But these angles here, now that you squeeze down a little bit because the lone pairs take up more space, I would write this as less than about 109 degrees. That means, it's not like it's 95. It's not that much less, but it's based on the tetrahedral angle, but a little bit less. It's actually about 107 degrees for ammonia. Okay. And finally, okay. And finally, in the case of water, okay, you have, again, from the Lewis structure, you have the 4 groups of electrons. I guess I could draw it. Well, let me draw it this. Here, I'm going to put the H's on regular bonds, and I'll just have the, kind of like going back. This is really a Mickey Mouse drawing. And this angle here, because the lone pairs take up even more room, and it is 2 of them, that this angle becomes about 104 to 105. But you could still write less than about 109 degrees for the bond angle. You should know, though, that this bond angle is smaller than that for NH3 because there are 2 lone pairs. And the electron geometry here, again, is tetrahedral because you do have 4 groups of electrons on the central atom. The molecular geometry is bent. It's bent. All right, so that was really all review, really, from last time. And now we're going to do the next one, which is what happens when you have 3 groups of electrons on the central atom. And if you take 3 balloons, and they're going to do this, I think, in lab this week, and tie them together in the middle, maybe next week, I'm not really sure, and tie them together in the middle, and they try to get as far away from each other, you get something like this. Now, if you look at what's going on here, not the best picture. So if you draw lines from the center out to the edges, the ends, this is 120 degrees. So this is the one that's 120 degrees. And if you take and connect these dots here, presumably you have, if you have atoms on the end there and the atom in the middle, if you connect all these, you will see that they are all in the same plane. So the atoms would all be in a plane. Yeah, the balloons and the electron clouds might go above and below the plane, but the atoms are all in a single plane. I could try to draw that here. I don't know. It's a terrible picture, so don't try to do that. Don't. Anyway, so this is a planar molecule, and in fact, the electron geometry is called trigonal planar. Trigonal because there's one, two, three things that are attached. Well, they don't. There's three groups of electrons. That's what makes it trigonal. And it's a planar molecule, hence the name trigonal planar. So we have to think about, what types of molecules would have geometries like this. Remember that the central atom also has to have an octet. So you have to think of the ways to get an octet with three groups of electrons. So how could you do that? And by the way, a double bond counts as one electron group because the two bonds of the double bond are pointing in the same direction. So we're really only interested in, groups of electrons in terms of which ways they're pointing. If you have two bonds together, they can't point in different directions. So we consider that to be one electron group. So can you think of a way, if I have an atom A in the middle, okay, how could I get an octet with three groups of electrons? Anybody want to suggest something? Can I have three single bonds? Actually, I can for one atom. What is the atom? The only atom that this would work for? Remember, incomplete octet? It works for boron. Okay, so that's kind of the exception. I would like to do that later, not first. But you could have a double bond, right? And what else could you have? If you had that, that's not an octet. That's 12. But you could have two single bonds, right? Then it would be 2, 4, 6, 8. That's an octet, right? So this is one way that you could get an octet with three groups of electrons. So this is two single bonds and one double bond. So I write 2 SB, 1 DB, and that's three groups. Okay, another way, what's another way? Is that the only way I could get an octet on that central atom? What else could I have? No, that if you had another double bond, that would be it. You'd have two groups of electrons. That's 8, right? 2, 4, 6, 8. So that's not. Exactly. You could have one double bond, one single bond, and one lone pair. And what else could you have? Yeah, that's right. And the sort of exceptional I'm going to write it underneath this one because it has the same geometry. The exceptional case is if you have boron. And boron can have an incomplete octet. Boron is good with 6 electrons. We call that incomplete octet. So I'm going to show you by example the first of these. Now, all 3 have 3 groups of electrons on the central atom. So all of these are trigonal, have an electron geometry. A trigonal planar electron geometry. So now the question is, where are the atoms? Right? So this first one, you have atoms at the ends of all of these bonds, because they're bonds. But here you don't have an atom at the end of that one because it's a lone pair. And here you don't have atoms at the ends of those either. Okay? So I'm gonna, like I said, I'll do this by example. NO3 minus. If you write the Lewis structure for this, how do you do that? Which of those is going to go in the middle? N. Why? Because it has a lower electronegativity. So you'll start by writing it here like this. Well, you'll start by counting up the valence electrons. You have 5, 3 times 6, and then you'll have 1 for the electron. That's 24 electrons, or 12 pairs. You'll do your single bond thing. 1, 2, 3. Now what? What do you do next? Lone pairs where? On the outer. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you check for octets, but you have no octet here. So what are you going to do? You're going to make a double bond. So you'll have N double bond O. And now you see that you have 3 groups of electrons. So you know you have a trigonal planar electron geometry. So that means to draw it really correctly with the right geometry, you have to draw it with 120-degree angles like that. You can't draw it straight here and have 90-degree angles over here and here. You have to draw it with 120 degrees to get the geometry right. And also, to be correct, you'd have to put a negative sign there. And also, by the way, how many other resonance forms would there be? Right. Which is to say that that second bond, that double bond, is sort of evenly spread around all of these. Okay, so that's kind of an aside, a bit of review. But now you see that you have an atom at the end of every one of those electron groups. So what is the molecular geometry going to be? Because you have an atom at the end of every electron group, it's the same. It's trigonal planar. So whenever you have all bonds, no lone pairs on your central atom, the electron geometry will be the same as the molecular geometry. And that's the case right here. In the example with boron, if I have BH3, okay. Boron has 3 valence electrons. I get 3 more from the hydrogens. That's 6. That's just 3 bonds. And like I said, boron is satisfied with just 6 electrons. We call that, as I said, incomplete octet. Does it what?
Yeah,
The valence is 3. So again, this would be 120 degrees. And this would have a molecular geometry that is trigonal planar. And its electron geometry is definitely trigonal planar because it has 3 groups of electrons. All right, so that's the first case back here. Now I'm going to take a look at this case. I have a double bond, a single bond, and a lone pair. Okay, now again, what is the electron geometry of this? 3 groups, trigonal planar. But now you don't have an atom at the end of one of them. And I'll give you the example of NO2 minus. We've drawn the Lewis structure for NO2 minus before. It's 6 times 2 plus 5 valence plus 1 for the negative charge. That's 18 electrons. That's 9 pairs. So I'd start like that. I took care of 2, 3, 4, 5, 6, 7, 8, 9. And wow, what do I have to do to fix this? Move a lone pair, make a double bond. And you should realize that there are 2 different resonance forms. They're equivalent. They have the same energy. One is not more stable than the other. And that the correct description is actually sum of each. But this does not show the right geometry here because it's pretending that this molecule is linear. This molecule is not a linear molecule. How do I know that? It has 3 groups of electrons, so I have to draw it. 1. A group of electrons is just a group of electrons that's pointing in the same direction. So like this double bond is a group of electrons. This lone pair is a group of electrons. This single bond is a group of electrons. I can't say bonds because they're not always bonds. There's bonds and lone pairs. And if you have a multiple bond, that counts as 1 group. Because they're pointing in the same direction. Okay? Lone pair is 1 group. Yeah, no, yeah, I do. Question?
say that the molecule has 1 electron instead of 2 neutral, instead of a lone pair, it's just a single.
Yeah, that's called a radical. And those are actually, we've heard about radicals, free radicals. They're always messing with your cells and destroying DNA and stuff like that. And that's why they tell you to eat a lot of, green vitamin C and stuff that it's a scavenges the free radicals and stuff like that. But no, that we don't do that here. That's for organic. You'll learn about that when you take organic. Yeah. Yeah. In fact, we don't even we never have an odd number of electrons. Notice I have not asked you to do NO2. without the minus, because that has an odd number of electrons. So we are not doing that in this class. All right, so how you would draw this is like this. Nice, you don't have to do a 3D thing with something coming out and something going back, because this is a planar molecule. This has an electron geometry that is trigonal planar, as I've said already before, but its molecular geometry is what? It's determined by the position of the atoms. So what do you think I would call that? Bent. Now, the bond angle, I should do this at the same time. Should have done it here. This bond angle for the previous example was 120 degrees, because they're trying to get as far away from each other as possible in the plane. It's like you have a piece of pie, you cut it in thirds. Everyone gets 120 degrees. But now you have a lone pair here, so that kind of squeezes down on this bond a little bit. So this is less than about 120 degrees, a bit less than 120 degrees, because the lone pair takes up more room, more space. Okay. So the electron geometry is trigonal planar. The molecular geometry is bent. And let's see. So that was that. And then the last type is the easiest type, because you have two lone pairs and just one bond. And since the geometry is determined by the bond, what does the molecular geometry have to be for a case where you have only one bond? It has to be linear. So this still has an electron geometry that's trigonal planar, but the molecular geometry or shape is simply linear. And just to give you an example of that, O2, that's 12 electrons, that's 6 pairs, 1, 2, 3, 4, 5, 6. There's not an octet on this one until I do this. So you could consider each oxygen to be, you could consider one at a time, the central atom being this oxygen. You say, okay, it's got 3 groups. It's trigonal planar. So I could draw this with my Mickey Mouse ears as the lone pairs. So you have a trigonal planar electron geometry on each thing. So you have 120, but really all this stuff is kind of stupid, because the molecular geometry has to be linear. Yeah, I already wrote it here. It can't be anything but linear, determined where the atoms are. So that's what we get with 3 groups of electrons on the central atom. This is the last type, the last thing. And there's really we're only doing 2, 3, and 4 groups of electrons. We don't do 5 and 6. The book has 5 and 6. We just skip that. The highest we do is tetrahedral. We don't go up to octahedral and all that stuff. So all I have left to tell you about is when you have 2 groups of electrons on the central atom. So that's like you have 2 balloons, and you all know what would happen if you tied 2 balloons together. They would form a linear shape, so that you would have a linear electron geometry, and you would have a linear molecular geometry. And here's a couple of examples that I could think of to tell you about. and one of them is CO2. So the only ways you could get this is if you have two double bonds. That's one of the ways. And the other way is if you have a double bond and a single bond, a triple bond, I mean, and a single bond. One triple bond and one single bond. So in either case, you have two groups of electrons on the central atom. And the only thing that can happen is you will have a linear molecular geometry. So that's kind of the trivial case. Yeah. No, no, no. So here you might notice that you have, I didn't put the lone pairs on the O. Oh, it's too many. So here, of course, you would see, you know, you have one. I'm just trying to show you it's a 180-degree angle, but it's not listening to me. Oh, well. And similarly here, it's a 180-degree angle. The HCN bond angle is 180 degrees. And here the OCO bond angle is 180 degrees. We have a linear electron geometry and a linear molecular geometry. Okay, so enough of me talking. I'd like you to take out this activity 4. And all you're going to do is the top part. We'll do the bottom part after. Some of these you've done already. This is one of my examples, but I want you to work on this sheet. Okay, and you're going to take some time to do it. Some of these I did last time. They might be filled in. You just look at them. You should be able to do all of these, the top part. Then we're going to talk about the bottom part after that. So there's all these different examples that I'd like you to do. Because really the only way you could understand this is to do it yourself. Okay, so this is a Lewis structure of HCl. No, it's the beginning of it. I have my 5 pairs, but you can see that the carbon doesn't have an octet. So if I do that, it still doesn't have an octet. So I have to do it again and make a triple bond. So now the next question is, what is the number of electron groups? It doesn't mean total in the whole molecule. It means on the central atom. Okay, and on the central atom, there are 2 groups of electrons. What does that make the electron pair geometry? That's like 2 balloons trying to get away from each other. They make a 180-degree angle. They're linear, right? They're pointing in opposite directions. It's linear. Now, you have an atom at the end of each of those electron groups. So that makes the molecular shape also linear. Okay? And it makes that bond angle, the HCN bond angle, 180 degrees. Okay? Is everyone okay with that? I think most people did do that. I saw it. Or the ones I saw. SO2. All right, now we have 6 and 2 times 6, 18, or 9 pairs. S has the lower electronegativity, so it goes in the middle. whatever, with single bonds in between. That takes care of 2. 3, 4, 5, 6, 7, 8. And the last one goes in the center because I have a leftover one. And now you see you don't have an octet, but I can take and make a double bond. And this is a perfectly fine Lewis structure. What some of you did, maybe without even really knowing why, oh God, is some of you took a lone pair from here and made another double bond. And this is allowed for sulfur because sulfur is in the 3rd period. But now, oh, sorry, I still had the pair here, which I forgot to put back. Yeah, there should be a lone pair there. Now sulfur has 2, 4, 6, 8, 10 electrons, which is allowed because it's in period 3 or higher. We call that expanded valence. And either way, whether you write the Lewis structure this way or this way, you have the same geometry answers here. By the way, you could not do this if this were an oxygen in here, because oxygen is in period 2, and you would have to write the structure of ozone, which is, very similar to sulfur dioxide, except that you have to leave it like this, because you cannot make 2 double bonds and a lone pair on an oxygen. You have to have 8 on oxygen. Okay, so now we can look for the number of electron groups, whether you drew the Lewis structure in either of those 2 boxes, whichever way you drew it, they're both acceptable to me. The number of electron groups is 3, right? So it might look like it's linear, but it's not, because you have this lone pair coming out of here. So if you were going to draw it with the right geometry, you draw it like this. And you would see that you have a trigonal planar electron geometry, as if you had 3 balloons. No. I could have drawn it like this, but I don't find that as easy. Yeah. Okay, the molecular geometry, what do we call that? Molecular geometry. Yeah, it's bent because it's literally bent. So it can't be linear because it has this lone pair up here taking up space. So it has to be bent. So the shape is bent. But what is the bond angle now? What is the OSO bond angle? So bond angles are between 2 bonds. It's between this bond and this bond. And it's about 120, but because the lone pair takes up more room, I would write less than about, that's what this means, less than about 120. Okay, so the next one. Thank you. Okay. So now we have CH3F. This is very similar to CH4. We have 4 valence, 3 times 1, and F is in group 7 or 17, 7A. So it's 7 electrons. So that's 14, right? Yeah. Or 7 pairs. Carbon would go in the center. 4 single bonds. One, 2, 3, 4, 5, 6, 7. Okay. So I'm good. This is my Lewis structure. Everything has an octet. The fluorine and the carbon, the H's have 2 electrons, which is what they need. How many electron groups? 4. 1, 2, 3, 4. That means you have what type of geometry? Tetrahedral. So really, I should be drawing it like this. Okay, with the dotted line going back, the wedge coming forward. And since you have atoms at the end of every electron group, this is also tetrahedral molecular geometry. And now the HCF bond angle, this angle here, just like all the angles here, what's the bond angle? It's the tetrahedral angle, 109.5. Okay, BF3, I've talked about this already before. 3, well, not BH3. 3 plus 3 times 7, that's 24. That's 12 pairs. One, you might start by drawing it like that because you don't know the geometry. Oh, sorry, BH3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, there isn't any more, but that's okay. It's only okay for boron. Boron is very much okay with having 6 electrons. We call that an incomplete octet, and it's the only element that you have to worry about does this. But now you see that you have 3 groups of electrons on this central atom, which means what is the overall geometry? It's like 3 balloons, right? So what is the overall electron pair geometry? Say it? Yeah, it's a planar molecule. Since you have an atom at the end of each one of those groups, the molecular geometry is also trigonal planar with a lovely 120-degree angle. H2CO, number of electron groups. All right, now for this one, the carbon is in the center. This is the skeletal structure. We have 2 electrons from the hydrogens, 4 here, 6 here, 12 electrons. That's 6 pairs. 1, 2, 3, and then I have lone pairs. So what do I have to do here? Make a double bond. Now, what is the geometry at that central carbon? How many groups of electrons? 3. Electron pair geometry? Trigonal planar. Molecular geometry. Now you have an atom at the end of each of those groups. So it's also trigonal planar. So if I draw this correctly, it should be drawn with a 120-degree bond angle. Doesn't ask for the bond angle, but it is 120 degrees. Oh, here it is right here. Okay. Carbon dioxide. How many electrons? Yep, we got 2 times 6 here and 4, 16. That's 8 pairs. Start by drawing single bonds. What next? Where do I put the next ones? Outer electrons, right? 1, 2's done. 3, 4, 5, 6, 7, 8, oh. What do you have to do here? I still don't have an octet. So this is my Lewis structure. Number of electron groups on the central atom. That makes the electron pair geometry linear. Since there's atoms at the end of each group, the molecular geometry is also linear, and that makes this bond angle 180 degrees. Okay. You want to try doing H2S? What does that seem like to you, H2S? What's above S in the periodic table? What? Oh, so this is a lot. This is the same Lewis structure as for water. You have 6 here and 2 times 1. So that's 8 electrons. That's 4 pairs. That's it. So what is the number of electron groups here? Yep. So what is the electron pair geometry? Now we only have atoms at the ends of 2. So what is the molecular geometry? We call it bent. Right. And what is that bond angle then? It's a little less than the tetrahedral angle. Something like that. All right, I want to do, you can do the rest of these at home. We've done some, like the NH3 we did already. CCl4 is very similar to CH4, but I want to get up to polarity. So I want to tell you a little bit about that. So polarity is pretty important because, so what I'm talking about when I talk about polarity of molecules is when the electron distribution is not even. It's not even all over the molecule. It has a part that's like a delta positive part that has less electron density, and then might have another part would be delta negative with more electron density on another part of the molecule. And what this all starts with is whether a bond is polar or not in the molecule. So bonds can be polar or not, and we've already learned about that. And we know that we can use the electronegativity chart to determine this. So for example, if I have an HO bond, like in H2O, and I look up on my electronegativity chart, which you would always get, the hydrogen has an electronegativity of 2.1. The oxygen is 3.5. This difference is 1.4. And if you look at this, that's not it. A handout I gave out a while ago on this, it's in this packet here. The bottom of this front page of the packet, it gives you the guidelines. And it says that if the difference in electronegativity is 0.5 or greater, then we say that the bond is polar. If the difference in electronegativity is 0.4 or less, then we say the bond is nonpolar. And my distinction is a little bit different from the books because they're wrong. Anyway, so here we would say that this is definitely a polar bond. And what that means is because of its higher electronegativity, that oxygen grabs negative charge to it. This delta means slight. So delta negative means slight negative charge. That's drawn to the oxygen and is drawn away from the hydrogen. And then we make an arrow that points from the delta plus to the delta minus. And this arrow we call a dipole. Okay. So it's just showing a difference in charge density of where you would have more electrons versus where you would have somewhat fewer electrons. Another example, if you had, say, a boron hydrogen bond, the boron, the electronegativity is 2.0, hydrogen is 2.1. This difference is just 0.1. So this is not polar. There are no slight charges on different parts of that bond, okay? So the thing is, you can have whether a molecule is polar or not, whether there is a region of a molecule that has slight negative charges and another region that has slight positive charges, that all starts with looking at the bonds. So in that same handout, I think actually this is on the activity 4 handout. So this is a part of the handout that you were just using. On the front page of that, which is like the second to last page in the packet, it goes through some definitions that I've just really gone over. But what I want to focus on here is a polar molecule versus a non-polar molecule. So a molecule that has a slight positive end on one end and a slight negative on the other end it would be polar, okay? And it would say it has a dipole. But there's two things that have to happen in order for a molecule to be polar. So to be polar, a molecule must have at least one polar bond. You can't have a polar molecule with no polar bonds. It has to have at least one polar bond. But the other thing that has to happen is it has to have a certain asymmetry so that the dipoles of its polar bonds do not cancel, because they can cancel. And I'm going to give you an example here. Okay, so here we have water, H2O, and I'm leaving out the lone pairs. I know it's a bent molecule, and I know that I have a dipole like this, that this is delta plus, and the oxygen is delta minus. So I have these two dipoles, one from each of these polar bonds that are pointing in the way I show. Okay. Here's another molecule, CO2, which I'm leaving out again, the lone pairs. And now carbon has an electronegativity of 2.5, oxygen's is 3.5. So the difference in electronegativity is 1. So CO is a polar bond. So I have a delta negative here and a delta positive there. But I also have a delta negative on that oxygen. So I have two dipoles like that. The thing is that water is a polar molecule, but carbon dioxide is not a polar molecule. And why is that? So what do you see about the arrows here that you don't see quite over there? How are they pointing? They're in exactly different directions, right? So the two dipoles here point in exactly opposite directions. And so they cancel. So there is no net. The net dipole is like the sum of the dipoles. There is no net dipole in CO2. So CO2 is not a polar molecule, but in water, so you have this arrow going up and to the right, and this arrow going up and to the left. So here it's like they're not like this, they're like this. So they're both pointing up. So what happens is that your net dipole points up. You could draw it like this. The net is like the you have the gross profit in a business and the net profit when you take away all the things you spent. It's like the net dipole is after partial cancellation, you have the sum of what you actually have, right? Yeah. What makes the what? It's not repulsion, they're dipoles. You have this, they point in equally and in opposite directions. The strength of these dipoles are the same because it's the same bond. They're just pointing in opposite directions. So if you add up these two dipoles, you get nothing. They cancel each other completely. Whereas here, you have the side to side. You can see that this one is pointing to the right. This one's pointing to the left. The side to side cancels, but they both point up. So the net dipole points up. And you would draw it like that. So we have a delta negative end of the molecule, and we have like a delta positive end of the molecule. So water is a polar molecule. So it's a little tricky for students in Chem 103 to figure out this business about when the dipoles cancel and when they don't. So I have this sort of chart that shows you the polarity of common shapes. I'm going to have to go over this, I guess, next time. But what you can see here is if you have a molecule like HCl, where you have only one dipole, right? If you look at the electronegativity difference here in HCl, you'll see it's pretty extreme. Cl has a 3.0 electronegativity. Hydrogen has a 2.1, so the difference is 0.9. So there is a dipole which points towards the more electronegative atom, the delta negative side. There's nothing to cancel it. So this molecule is polar. Okay, so a diatomic molecule will be with a single dipole will be polar. There's nothing to cancel it. Here's a case that's like CO2, where you have equal and opposite dipoles, and they will cancel. And the molecule, if there are two identical bonds, the molecule will be nonpolar. Now, if you had two different bonds, like one was a CH and one was a CCl or something like that, then they wouldn't cancel because one would be much stronger than the other. This is the case for ammonia. NH is a lone pair. It's not shown up there. But you have three different dipoles here, and they're all pointing up. But the side-to-side aspect of those dipoles will cancel. So the thing I want to emphasize is there are only these few types, really, of situations that can arise. So if you look this paper over the weekend after the exam, and try to think about what's going on here with these different charge distributions, I will spend a few minutes on it on Tuesday next week. Anyway, I think I should probably have some kind of Zoom session. I don't know. I feel like do you want to do it tonight or tomorrow night? Tomorrow. What's a good time? I mean, I guess I could try for 7 again. What'd you say? 11 PM? No, I can't do that. Let's go for 7 again tomorrow night, and I promise to be there.
7 p.m.
Yeah. I also have office hours. And none of this stuff is on the exam, so you have some more time to study it. Hi.
Do you be holding another session on Thursday? I mean, Wednesday? Is that what you had
So-
said? I missed it. What's on Wednesday? Oh, okay. I'll ask my questions then.
No, you can ask me now.
One of them I kind of wanted to go more sort of in-depth explanation, but so for the line spectrum, that's
Which
when
one are we looking at? Okay.
for number 2.
Yeah.
I can look that up. I just figured I'd ask you now. Is that when are they ejected? Because they're
No.
showing up, or when they move from
Yeah,
higher to
yeah.
lower, okay, yeah. I know it was one.
Hello.
Is there any chance you could record the Zoom tonight?
I could what?
Record the Zoom tonight?
I could try. I have one of them up there, you know.
Yes, I did watch that.
Yeah.
I had to
alright.
leave last night.
Okay. Yeah.
Cancel out. They're
Yeah.
facing opposite.
Have you ever learned about vector addition?
I didn't take a chem class.
That's not chem, it would be math.
Nope, didn't. What class would that be? Like,
I don't know.
I took
So-
a lot of calc.
Oh, here, take it. So do you have lab now?
In a bit, I have bio. and just-
So like you have. I've office hours today, so. I think, like, from now until like 1:30, then there's a break. But I'll probably be there.
In the event that you do get. I don't know.
Oh, tomorrow, yeah, I probably can even get someone.
Okay, so I'll still plan on it no matter what.
Yeah, I think so,
right.
I could always email.
Thank you.
So like if you have, like in water, you have 2 dipoles that point this way.
Yeah.
So what you learn when you learn about vector addition, the vector is got a strength, which is like the length,
Right.
and it's got a direction. You can translate a vector from, so if I translate this vector to over here, then the sum is what happens when you do the end to end. So the sum would end up being that. You see how the side to side cancels out, but you end up with a vector in this direction.
How did the side to side? Because they're both on either side.
One is probably not. The side to, look, this vector, okay, every vector has a portion that's this way and a portion that's that way.
Yep.
So this vector has a portion that's this way. So this is actually the sum of this and this. Then you have another vector that's got, that's this thing,
So, no, it's funny because there's the.
that's this. and
Oh,
this.
I
So the
see.
side to sides cancel and you.
So it's like positive and negative. Okay, like it's like opposite sides.
Oh, you have your own way. It's like you got it now. It's good.
Okay, sounds very complicated.
It's fine. Everyone has their own way of looking at things.
Okay. So why does it go up after this happens? What were you saying?
Well, when you do this vector addition, you translate the vector. So this and this, you translate one, you take this one, you move it over so it's head to tail.
Right.
And then you go from the beginning to
So
the
they'll come
end.
in, like, you know that.
And you can see that you don't have any component
Yeah.
that's side to side, you only have a up
Go
component.
pull out, like, only it's
I
like-
don't know, it's not that easy.
I'll look at it.
It's really not that easy.
What's that?
Have a good one.
You too.
Age. What is that?
For the pods?
Yeah.
No, yeah, it is,
Yeah.
yeah, he comes downstairs, that's the sideboard.
Yeah.
But they do, yeah, they have a B and C, and then C one's cardiac hold,
Yeah.
and then A and B are the ER.
Yeah. Yeah.
What are you
I
talking
also
about?
think
I'm working in the ER.
I probably get some notes from the doctor as well too.
And it's nice too, because if you get to like ask, like to come in, they'll probably let you do shadow time, like if you would shadow some of the PAs once you get to know them, you're like, can I come in during the day of the day off and shadow you or something like that?
Did you take classes while you were doing that?
Yeah.
And how was that? Like it's hard.
I was younger, so I was, and I'm not like. So like, I probably couldn't do that now.
Yeah.
It was just 3 years ago.
Maybe
But
I
it
just
was-
like sticks, because I have, like, some schools count my experience in the hospital already, so it's already 960 hours.
It depends, yeah, if you're doing
Something.
patient care, yeah. I'd have over 5,000 patients per hour, so I'm not doing that well.
Yeah.
I'm starting to shadow, I have, my work at work. So like one of his big friends, she's letting me shadow her at the OR, starting that. I'm gonna call it somewhere you're flying.
Yeah, oh, really?
Yeah.
Oh, nice. So,
Well, yeah, you can still do whatever you want.
fish here.
Cause the bad thing is that they don't start till the next holiday.